All series long, we've printed a single accuracy number and nodded along. But here's an uncomfortable truth. One train test score can lie to you, split the data a different way, and the number jumps around. This episode is about actually trusting your results, proper evaluation, cross validation, and the metrics that matter when plain accuracy isn't enough. The problem is the lucky split. When you carve off one test set, you get exactly one score, and that score depends on which rows happen to land in the test pile. Get an easy split and you look like a genius. An unlucky one and the very same model looks weak. One number, far too much luck. Cross-validation fixes this. We chop the data into k equal folds, say 5. Then we train on 4 of them and test on the 5th. Then we rotate, a different fold becomes the test set, and we train on the rest. We go around until every fold has had its turn as the test set. That gives us 5 scores instead of 1. We report their average, a far more stable estimate of true performance, and their spread, which tells us how sensitive the model is to the particular data it sees. Mean plus or minus, a standard deviation beats a single lucky number every time. Now, accuracy itself can mislead. Imagine a disease that affects 1% of people, a lazy model that always says healthy is 99% accurate, and utterly useless. With imbalanced data, accuracy alone hides the failure completely. We need sharper tools. So we split the errors apart. Precision asks, of everything we flagged as positive, how much really was? Recall asks, of all the true positives out there, how many did we actually catch? They trade off against each other, and the F1 score blends them into one balanced number. And which one matters most depends entirely on the cost of a mistake. For a spam filter, precision, don't junk a real email. For cancer screening, recall, never miss a real case. There is no single best metric. There is only the right metric for your problem. In Scikit-Learn, cross-val score runs the whole k-fold loop in one line, and classification report prints precision, recall, and F1 for every class at once. A confusion matrix shows exactly where it confused things. Let's write it. Here's the program. One page, every line visible. It's short, but it replaces a shaky single score with numbers you can genuinely trust. Let's read it. The imports, a dataset and a model, random forest will do, and then the evaluation stars, cross-val score, classification report, and confusion matrix, all from sklearn.metrics and model selection. We make a classification dataset and create the model. Notice we are not even fitting it ourselves yet. Cross-validation is going to handle the fitting fold by fold for us. Here's the heart of it. Cross-val score handed the model, the data, and CV equals 5. In one line, it runs that entire 5-fold loop, training and scoring 5 separate times, and hands back the 5 scores. We print the mean of those scores and their standard deviation. Now, instead of one fragile number, we can say something honest. The model scores around this much, give or take that much. That little plus or minus is the whole point. For the richer view, we do one ordinary split, fit, and predict, then call classification report. Outcomes, precision, recall, and F1 for each class. The full breakdown, not just one blurred average. And we print the confusion matrix, the little grid of predicted versus actual. The diagonal is everything it got right. Everything off the diagonal is exactly what it confused with what. It's the most honest picture of a classifier you can get. And that's evaluation done properly. Cross-validate for a trustworthy score and look past accuracy to precision, recall, and the confusion matrix. Trust your numbers and you'll trust your model. Next time, we use these very scores to automatically hunt for the best settings. Hyperparameter tuning,